So let's go quickly over an example, right? So it's a little bit time-consuming to construct a two-dimensional Laplacian operator. So let's actually go to MATLAB and construct a simple one-dimensional Laplacian operator, and see how stable this operation is. So a one-dimensional Laplacian operator is actually pretty easy to construct. So let's say if I have a delta x in the middle, I'm basically looking at this one. In the middle, I have -2 over delta x squared, right, all the way to here. And on upper and lower diagonal, I have 1 over delta x squared. Okay, so this is assuming I have a known boundary condition, right? So basically, the value here and the value here is some known function, a known value that can be moved to the right-hand side. So if I have this, let's see. For example, if I take n to be 100, and my delta x is equal to 1 divided by, so let's say the size of the matrix is n, which means my delta x is actually equal to 1 over n plus 1, right? So I have number 0, 1, up to n, and my last grid point, which is on the, so this is the known boundaries, is 0 and n plus 1. So my delta x is 1 over n plus 1. This analysis always has to be done to figure out what's the relationship between the delta x and number of unknowns. So I have my delta x, and my a is actually, let's use the same technique we used to construct it. So first of all, let's set a to be -2 times identity. So what you see is I get a matrix that has -2 on the diagonals, right? So now let's a is equal to a plus a diagonal of 1s, n minus 1 and 1. So that's basically a vector of n plus 1 ones. And the second argument of diag, so if I just make it like that, it won't work, because matrix dimension must agree. So a diag of a diag, basically it turns a vector into a matrix and the matrix into a vector. So if you give diag a vector, it gives you a matrix with the given vector as diagonal entries. If you pass a matrix, it gives a vector of the diagonal entries of the matrix. But there is an additional argument in diag that you can give, is to shift this diagonal above or below. So if you give it to 1, actually it'll create not an n minus 1 by n minus 1 matrix, but an n by n matrix with the given vector as diagonal shifted up by 1 entry. And you can also shift down by 1 entry by providing a -1. So what you get is the tridiagonal matrix we want. And then A is equal to A divided by delta x squared. So that gives us the matrix we want. So let's, for example, compute the Eig of A. Well, the answer is 100 by 1 vectors. So that's all the eigenvalues of A. And if you plot it, so that's kind of the distribution of all the eigenvalues of A. And in order to figure out the stability, which one should we look at? Towards the right. And why is that? Yes, we look at the one with the smallest magnitude. So here, all of them are negative, right? So we want to actually look at the one that is closest to 0 always. Okay, so what we can see is it has a lot of very, very negative, very large magnitude eigenvalues, but then the one closest to 0 is like -10, right? So actually we can say, if we take the absolute value of Eig A and then take the minimum. So that is the one that determines stability. And if this is as large as 10, we actually have a very stable system. All right, it's very, very stable.